right, so today we have Max Hübner, who will tell us about SymTrees and Symmetries. Take it away.
Thanks for the introduction, Julius, and also thank you for the invitation. Right, today I'm going to be talking about SymTrees and Symmetries. One has 2 syllables, the other has 3. And so this talk is going to be based on 2 papers that appeared in the second half of last year and that I wrote in collaboration with Florent Baum, Miriam Svetic, Jonathan Heckman, Ethan Torres, and Andrew Turner. So this talk is going to be about collections of symmetry TFTs, interfaces between symmetry TFTs, and how to physically interpret these in certain cases. And the SymTFTs and their interfaces are going to be arranged into a tree-like graph. And this is where the name SymTree comes from. So to best set up these ideas, let me recall the standard SymTFT sandwich as going back to ideas of Fried, Moore, and Telemann. So if we're given a quantum field theory in d dimensions, then in many cases we can expand it into a relative quantum field theory, here in red, also in d dimensions, a topological boundary condition in light blue, also in d dimensions, which live on the boundary of a d+1 dimensional slab, which supports a topological field theory, the so-called SymTFT. And the situation we're going to be interested in today is where this quantum field theory comes with a collection of parameters, which I've labeled lambda here. And in this case, we get a family of sandwiches, one symmetry sandwich for every point in parameter space m lambda. Of course, the lesson of the decade has been that symmetries are topological. And so if I simply perturb lambda goes to lambda prime by some epsilon, then the SymTFT is not going to change on me. However, what I can do is consider infinite distant limits in parameter space, go to the boundaries of parameter space. And in this case, it might happen that certain operators are suppressed, decouple. And that, for instance, the red physical theory here decomposes into a collection of subsystems which no longer locally interact. However, they can still topologically interact, and the job of the SymTree will be to precisely capture these topological non-decoupling. So the goal of the talk is to study decoupling limits with topological non-decoupling. And the examples I'm going to consider are going to be string theory motivated. We'll have access to some extra internal geometries. And the limits we will consider in this context are those where localized degrees of freedom in the internal space are spatially sequestered and separated by larger and larger distances. Let me also say that SymTrees have other applications. At the end of the talk, I'll come to some applications on no-global-symmetries in quantum gravity. But then end of very recently, the Oxford group has introduced the club sandwich. And the club sandwich studies a topological interface between 2 SymTFTs. And in this context, SymTrees have been used to determine gapped infrared phases of 2D theories with a given symmetry S. So given these multiple and very different applications and motivations for SymTrees, I'm going to begin with a bottom-up field theory discussion. Then we'll do a top-down discussion, and then we'll discuss an example at length. But before I press on, let me quickly check if there are any questions regarding where the talk is going and the outline. Okay. So, what is a SymTree? As already stated just now in the introduction, a SymTree is a collection of SymTFTs, which I'm denoting collectively by S, as unfavorable coloring. And They'll be in d+1 dimensions, and a collection of boundary conditions. Here I'll be distinguishing three types of boundary conditions: topological boundary conditions, light blue, physical boundary conditions, red, and junctions. These will typically be mixed, topological partially and also partially physical. The first two types are boundary conditions for exactly one SymTFT. And the latter type can be a boundary condition for multiple SymTFT, hence the name. And so the pictures we'll be drawing throughout the talk roughly look like this. We have in light blue, so I'm on the left-hand side now, in light blue, purple, and red, there are d-dimensional structures, and in between these are d+1 dimensional. Each of these slabs in golden are symmetry TFTs in their own right, and each of the colored edges are boundary conditions. And so here I've drawn an example which would be a QFT-like symmetry, where there's exactly one topological boundary condition and multiple physical ones. Right. But in principle, okay, I'll say a few comments in a second. There is an equivalent presentation of this. I could simply fold it if I really want to just talk about interfaces between two SymTFTs. And in this case, I would just rewrite the setup as there's a interface between the SymTFT labeled 1, 2 and the disjoint union of the SymTFT labeled 1 and 2. So this is a very general structure, and so some comments are in place. So I could change simply the number of topological boundary conditions versus the physical ones I've imposed at the external nodes of my symmetry. And indeed, purely topological boundary conditions have been applied in generalizing Landau's paradigm. When we come to gravity, there is going to be nothing like a global form, and so this will be reflected in there only being red boundary conditions. Junctions could be, they don't have to be mixed, they could either be purely topological or purely physical. The valency of a junction also doesn't need to be larger than 2. I've drawn, in some sense, the simplest example above, but you can do higher valency and you can build a bigger tree. But today, and this is motivated from their origins in string theory, I'm going to focus on symmetries with finite depth, and they're going to have no loops. From a bottom-up perspective, one might want to start playing interesting categorical games and allow for these kind of structures. To also,
so you said you'll exclude it, but what would a loop mean here? What would be the interpretation of the loop?
How do you regulate in the 75%?
Sorry, did someone? Okay, no, just
so no, it's just a different
at the moment
thing,
I'm saying nothing more than there being, you draw a picture with a loop, and then you would have a boundary condition which in some sense has, I would say, two decoupled set of symmetries which don't really talk to each other. And so you would reflect this already existence of some subsystem as having two, you would say independent leaves growing between any of the colored edges. Right, but
okay, fair.
So the reason that it will not appear in string theory constructions is because there's some notion of a radius, and where these structures will come from is I'll be scanning over radii, and so in this procedure they just do not occur. Okay.
Okay, thanks.
But thank you for the question, Julius. And okay, so I was just going to finish off these general comments by saying, well, sometimes I'll just draw the symmetry as a tree. And this is just notationally a bit more convenient, but you can also always keep in mind the pictures I drew above. Okay. So whenever we talk about SymTFTs, there is always a discussion of defect and symmetry operators. So defects typically extend between boundary conditions, and topological operators typically live as, well, yeah, topological operators in the bulk of the sandwich. And so we can consider very similar situations here. So I've drawn some examples. There is basically any configuration that you could come up with. So for example, I'm considering here a topological operator n, and this is it is located purely in the bulk. And so there are now, for topological operators, there is now certain equivalences because I can topologically deform them. One topological operator will have different presentations inside of the SymTree. I can try to, for example, deform it across a junction. It might split into two other topological operators and possibly still be connected back to the junction it passed through. There, this connection might itself realize some junction topological operator. And similarly, I could start considering topological operators in all of the different SymTFTs, right? After all, they're SymTFTs in their own right. And then, roughly speaking, the set of all topological operators is going to be the operators of all of the systems modulo equivalences of deformation. And in this question in the chat, are these SymTFTs just a discrete collection, or are they further smoothly parameterized? So I will assume that I have that into the tree they'll go into the tree there'll be a finite number of SymTFTs. Does that answer your question?
I guess the question was in relation to the first slide that you showed, where you had this parameter lambda, and then you were talking about taking limits.
Right. So I will only ever consider this. Okay. So the goal of that figure was to motivate how a symmetry might come about if you don't have one to begin with. Because typically we start with a sandwich and that's it.
Mm-hmm.
And now I wanted to say that I can take certain limits in moduli space where the symmetry structure is going to be more accurately described by a symmetry. In no sense I'll be, right, particular because in a small neighborhood, right, these symmetry structures are unchanged under perturbation. There is, at least locally, no trivial fibration structure. So if I'm focusing on an open set of parameters, I can always talk about one SymTFT or one SymTree. And in this sense, I will be focusing exactly on one of these structures.
So is the idea that on a generic point, say on your first manifold M, you have a normal sandwich, but then you go to some limit in this parameter, and then the sandwich becomes a symmetry like this?
Yeah, so the way that I will motivate this later is that in this picture here, consider taking these two physical boundary conditions and contract these two legs.
Mm-hmm.
And then the purple and the red will be stacked.
Mm-hmm.
And they'll be coupled by things which in the current picture run between the two boundaries. So here's, I've drawn a picture on the right-hand side. So these kind of guys could be heavy states which have decoupled and in the symmetry are now shown as defects. And so this is, I can arrange for a limit. For example, some masses go to infinity. And in this case, to capture these kind of heavy objects, I would want to expand the theory into the symmetry. Conversely, if I want to now include what I've drawn here as this brown string back into the physical spectrum of the red boundaries, the relative theories, then I'm going to contract the symmetry and stack the purple junction with the red boundary conditions.
Mm-hmm. I see.
And maybe to give you more intuition, the example I'll discuss later is the one where each of these physical boundary conditions is a stack of branes. And so these themselves will host world volume dynamics, and there'll be open strings in between them. And if I want to describe the system at energy scales but below the mass scale of the particle introduced by the open string, I'll be tempted to, I'll want to describe this open mode as a defect in my theory. And then it's exactly like this.
Mhm. Thanks.
Okay. And so this is also the motivation why one draws these defects maybe as strings in this case. But in general, right, so we've just talked about the symmetry operators. And now the defect operators are very similar. Here you have some sort of junction string, some string junction, which you might want to stretch between the boundary conditions. You could have something just running between the physical boundary conditions. This is the picture we just discussed. Or there could be something just running between the junction and the physical boundary condition. So all sorts of configurations are possible, and we will give them meaning momentarily. So there's a collection of standard operations one encounters in studying SymTrees. The one I just discussed is where, right, we said in the introduction, maybe I'll go to some special point, some infinite distance point in my parameter space. And in this case, the relative theory decomposes into a collection of locally decoupled theories. And to reflect this, I can pull these two decoupled theories out, and they have their own set of symmetries. So I make them manifest in terms of these two SymTFT branches. And right, and so that's the SymTree growing roots, as I like to say. And maybe in terms of actions, this is how it would look. I start with some action. There might be some mixing terms. I take the limit. There's some suppression scale. I suppress these away. The action decomposes into this direct sum. And so I might want to start talking about the symmetries of each summand individually. And then the topological coupling in between these is going to be reflected by the fact that they all still connect through this D+1 dimensional structure. Now, if one studies SymTrees, then one might also start trying to rearrange them. So here I've drawn the standard associator picture, where I have the external nodes are a single topological boundary condition and 3 physical ones. And I could have SymTFTs running in various ways between them. And then I might rearrange the trees as shown. So I get a junction going between theories, 1 and 2, 3, and a junction going between theories, going to theories 2 and 3, or the other situation, we have a junction going to theories 1 and 2, and a junction going to theories 1, 2, and 3. And in principle, it's possible that such rearrangements give some phase in the partition function and characterize some notion of generalized anomaly, although we'll be not encountering cases of this kind today. And so different way of viewing this is I can also collapse everything as I showed above just onto a straight line. We might be talking about disjoint union of SymTFTs. And in this case, I'm pulling junctions through each other. And these are codimension 1. And maybe you want to view the SymTree as a topological defect in an ambient trivial theory. And then there might be some phase upon interchanging these junctions, which live inside of the SymTree. Okay. And then finally, what we often do in the context of the SymTree is to collapse the slab and go back to a d-dimensional presentation. And because each of the branches of the SymTree are SymTFTs themselves, these operations exist. They need to be interpreted given the physical system, but abstractly you could just contract them, and so relate a whole set of SymTrees and its contraction. And so here I've sketched this tucking in that I just discussed with Antoine, where I can go from a SymTree back to a standard sandwich. Okay. But so I've now just abstractly characterized some of their properties, told you what ingredients are and how manipulations of these might look like. But let me explain to you where they come from in concrete string theoretic setups. But let me also quickly check if there are any questions. Okay, top-down approaches. So let me briefly recall previous work in the literature. In particular, this work by Fabio, Federico, Iñaki, Saga, and Sakura, where they explain how to derive the symmetry sandwich in a geometric engineering context. So the geometric engineering context that we'll be considering is that of either type 2A, type 2B, or M theory. And it's going to be placed on a purely geometric background X, which is the cone over partial X. In this situation, there is a well-known prescription. Okay, so here's the picture. I have a cone with my singularity at its tip. The whole space is X, and its link in light blue is partial X. In such setups, there is a prescription to derive the SymTFT of the QFT that is being engineered by this geometry. And here I've indicated it schematically as saying I need to integrate over links of my geometry. That's the integral. I need to integrate, and the integrand is basically set by the supergravity theory in question. And then there is a restriction to the topological sector. And so this has been shown to work in many cases. It's very powerful in studying high-dimensional SCFTs, which are basically defined via which can be defined via their geometric engineering construction. And so this has been great success. And so from this perspective, the question or the setup in which SymTrees arises, what happens if I, instead of considering a cone, consider now a space X which is only asymptotically conical? So this space is going to have possibly multiple singularities. 2 I've drawn in this picture. And each of these singularities can, on vanishing cycles, support localized degrees of freedom. Each of these singularities has their own little cone here, right? So each of these singularities I could study using some local model. And then only if I start going radially more outwards, I notice that at some critical radius r star, that these 2 singularities sit in some common space. And then I go off to infinity and right. And that's the second half here. So for each of these segments where, let me draw it like this. For each of these little cones, so here's the first one, here's the second one, and then there's this beyond the line that I just drew. I can apply the construction that I just mentioned again, and for each of these things, I will build a SymTFT, and this is where the branches of the SymTree come from. And so what I'm going to ask is, what is the general prescription in terms of mapping from these now non-conical geometries, multiple singularities, onto something like a SymTFT? What do we mean with that something, and how does this construction work? And so the first and naive thing to do is to say, okay, maybe I want to do exactly the same thing. I want to integrate over radial shells of the taking supergravity degrees of freedom into account, and then restrict to some, it crashed, and then restrict to some topological subsector. 1 second. Okay, it's going to restrict to some topological subsector. So, but that doesn't quite work. It's not good enough because, oh no. Because as I motivated before, the junction is still partially topological and partially physical, so we need to do a bit better than just restricting to the topological subsector. Okay, 1 second. this is not working. Thumbnail sees it.
Maybe you can just quit the app. It's back. Nice. Very good.
This has been the experience in the past, although it hasn't been letting me wait that long. Okay, yeah, sorry about that. Anyway, okay. So I was trying to explain how to go from this asymptotically conical situation to something like a SymTFT, which will be the SymTree. But essentially the idea is still correct. Yes, I can integrate over radial shells, and this is what's going to land me on the SymTree structure. And so here's the general idea drawn out in pictures. So I've separated out these two conical parts, which we understand very well using the previous prescription, and which give you the SymTFT parts of the SymTree down here. And then the thing to realize is that the structure mediating between these is something like this pair of pants situation. This cycle, okay, this pair of pants might have some internal cycles, and expanding supergravity forms might get like extra gauge degrees of freedom. And the examples we'll consider, they'll be U1. And these are the things which are going to go into the junction. And besides realizing that there's this pair of pants happening, it'll essentially be exactly the same prescription. And this is formalized all a bit better by using filtrations of the geometry. Oops, let me also get rid of this. There. Filtrations of the geometry, where, okay, I mean, there's this pair of pants in the middle, but this is like some properly extended thing. And if I really want to push the idea of integrating supergravity terms over radial slices of my geometry, then there'll be, this is best seen in the above picture, then there'll be some critical slice here, where the two neighborhoods of the singularities meet and combine into the larger one, which dominates the radial slice afterwards. And this critical radial slice is exactly the deformation retraction. Oops. Come on. It's exactly the deformation retraction of this pair of pants that I've drawn here. And so this is what I'm telling you now. So the junction fields are going to derive from simply the cohomology groups of this space V. And the junction fields will have two purposes. Some of these will mediate gluing conditions. So let me explain. So here, U R smaller than R star is the boundary on the left-hand side, drawn here. U R larger than R star is the boundary on the right-hand side. And so when compactifying over, these are radial slices, when compactifying in supergravity terms on them, they will contribute fields themselves. These are going to be fields of the SymTFT. And now I'm going to have to relate them at the junction. And the way to do this is to map the cohomology profiles that I'm identifying or getting these from into this pair of pants. And if they map onto the same thing, then the symmetry TFT fields are going to glue across the junction. And so the SymTF, so the modes that the junction fields that I get from the image of these two maps are going to formulate gluing conditions between the in-running legs. Everything that's not fixed by a gluing condition is going to remain fluctuating. And so these are the degrees of freedom fluctuating on the junctions. And they can be characterized via this co-kernel. All junction fields modulo those fixed by boundary conditions. Okay. Now, the point of giving this abstract discussion was that it's exactly that. It applies to very many different cases. And as soon as you have a geometry, you can just crank the prescription. But maybe to supply some more, show you how this works and to apply some physical intuition, I now want to discuss an illustrative example, which is simply going to be a joint Higgsing of 7D superyoung Mills theory. But before I start with those details, let me check if there are questions on the geometric engineering prescription. Okay, maybe they'll come up when we discuss the example. And so please don't hesitate to ask. So the example is going to be M theory. We're going to start out with M theory on a ADE singularity of A type and rank n-1, C2 mod Zn. And the field theory that is engineered by this cone is a 7D superyoung Mills theory with gauge algebra determined by the Mackay correspondence to SUN. And instead of studying all of the symmetries and so on, we're going to focus on a particularly informative part. And that is essentially going to be simply the SymTFTs, the field content. So there's just this one derivative term. So the 8-dimensional SymTFT of the 7D superyoung Mills theory is going to have this contribution, B2 cup D or delta C5. And the B2 is going to be the background field associated to the center Zn symmetry of the 7D superyoung Mills theory. And the C5 is its magnetic dual. And so here's the picture of the geometry. We simply have X mod Zn. It's a cone over S3 mod Zn. This cone has a Hopf circle, and this Hopf circle is the geometric analog of the Zn center. And so this Hopf circle is going to inform us about properties of this center symmetry and its backgrounds B2, C5. And the standard, yeah.
Where do you get the B2 from?
Where do we get it from?
Yeah.
Yeah, so I get it the following way. In this case, the relevant supergravity theory is 11D supergravity, and I have G4. And the length series S3 mod Zn has a torsional 2 cohomology class. And so there'll be a expansion, which will be B2 cup this torsional 2 cohomology class.
You have n-1 of them, no?
No.
What is this torsional?
Right, this torsional group is a Zn. I'm taking the generator as an any-dimensional reduction. I'm expanding G4 with it, and B2 is going to be valued in Zn. So depending on what value B2 has, I'm going through the Zn group. So I'll have a single Zn valued field B2.
Mm-hmm.
Yeah.
And C5?
Same thing with G7, magnetic dual.
Mm-hmm. I see. Okay. Thank you.
Thanks for the question.
Max, I don't know if it matters, but are you in the ALE or ALF regime?
I'm in the ALE.
Okay.
I think it would matter. If I have a finite size circle at infinity, then things change a bit.
Well, the gauge group would change, I guess, right?
Yeah, exactly.
UN or something. Right. Okay.
Yeah.
All right. Thanks.
Thanks for asking. Okay. So this is roughly the data that we're going to now keep track of and derive a symmetry from. So a joint Higgsing. Okay, there's a type 2 dual situation to the geometry I described, and that is simply a stack of D6 branes and D6 branes. And I'm now going to separate the stack of D6 branes into a stack of N1 D6 branes and N2 D6 branes, or just rewritten everything in terms of geometry. I'm going to do a partial resolution. I'm going to do a partial resolution. Whatever. I'm not going to get rid of it. I'm going to do a partial resolution of X to X tilde, where the ADE singularity is deformed in this way. This Higgsing on the Lie algebra is going to simply be a Higgsing of this sort. And so the geometric comic of what's happened is that I've taken my singularity and I've deformed it into two singularities. And okay, in this is the type 2A M theory, the picture relating these two frames. And the resolution has introduced one exceptional curve into the geometry fibered by this ALE circle. Okay. Now, given this geometry, I want to derive the symmetry. And so this is how I'm going to decompose X tilde. I'm going to first consider locally, this on the left-hand side, the neighborhoods of the two ADE singularities of rank n1 minus 1 and n2 minus 1. These are going to be, well, themselves, they are ADE singularities, so they're a cone over S3 mod Zn and Zn2 topologically. Then, due to the origin of coming from Zn ADE singularity, I know there's this pair of Penn's tube, which goes between these two boundaries to the larger boundary, with characterized by n1 plus n2, and then things go off to infinity. And I want to map this onto this symmetry. And so a bunch of the steps are straightforward and basically trivial. So the physical boundary conditions are going to be determined simply by the singularity, and they are SUNI vector multiplets. There they have center symmetries. And just by doing the standard SymTFT geometry to SymTFT game for the cone parts here, so this, and this, I learned that there are these golden branches of the tree, which have, all of them have a copy of B2, and I'm labeling by N1, N2, and just N, the sum of N1 and N2. And so these are the terms that on the branches of the symmetry we're going to keep track of. And now the only thing to do is to tell you a bit more about what's happening at the junction. How do these TFT fields, how they relate by the junction, and does the junction support any degrees of freedom? I think I've written these questions out here. Exactly. Are there degrees of freedom at the junction? And what are the boundary conditions the junction imposes on the SymTFTs?
So this you can do for any value of n1 and n2, right?
Correct.
So you get the partial order structure of partitions
Yes.
of n. Now, do you give any significance to intermediate steps where n1 can have the same phenomenon again, so that you'll get a resolved tree where
Exactly. So this is how I build more general examples where I could build symmetries of depth larger than 2 in this case. And each of the branches and the junctions would exactly be characterized by such a partition. I think these cases are basically handled by stacking multiple of the ones that I'm discussing now on top of each other.
Yeah,
Yes.
you get, it looks like the geometry of symmetric products.
Yes, I agree with that.
Okay, thank you.
Thanks, Ami.
And do you get any trace from like the action of the Weil group, like exchanging two throats, or this is?
I guess this would be a symmetry of the symmetry. I'm sure you can talk about these. I wasn't going to.
I see. Thanks. So in this case, sorry to add yet another question.
No, go ahead. Questions are good.
In this case, if we do split one of the singularities further, then I guess
Yeah.
we make the dot purple, and then we create two red dots. And then there's this question of the crossing. So here it looks like this should be without picking up any phase. Is this correct?
That's exactly it's
okay. Good.
So these cases where I have a geometry and I'm picking one way to scan over radial slices. Picking such a way gives me a symmetry, and it's as you say, if you just take a different way of scanning over radial slices, there's no sense that you're going to pick up a anomaly because you're exactly describing the same system.
Okay, thanks.
This is why in geometric engineering context, this phase doesn't pop up.
So can I ask one additional question? I noticed that in the pair of pants, there has been a different genus in your drawings. I don't know if this is relevant or what does it correspond to?
So, well, I need to allow for this situation. Well, okay. In principle, it just could be there, right? And so here I've drawn exactly one genus to reflect that we will find a compact 2 cycle and a corresponding 2 co-cycle. And reducing your supergravity degrees of freedom on that is going to give you exactly one U1 field. This is, of course, the U1 you expect from the Higgsing. Did I? Right. There's the U1 in purple, which I've sneakily not labeled because I haven't derived it yet. But this is exactly what the genus contributes. Well, not exactly a genus, just for the picture I've drawn it. But this is what additional compact curves that you might not see in each of the legs contribute. They contribute additional, in this case, U1 degrees of freedom, which are going to be localized at the junction.
Thank you very much.
Thanks for the question. Okay. And so here is exactly this picture that I had just mentioned to Julius of how to think about what we're doing. So the purple lines, you can think of level lines for a function. And this is going to be our radius function. So we start out at small radii where we have radial shells, which are the disjoint union of length spaces linking each of the singularities. Then these radial shells grow. They're going to touch, giving you this figure 8 situation. And then this crossing point is going to resolve, and you're just going to be left with a larger radial shell, which is S3 mod Zn. And all the magic of the junction, which I'm drawing here again, lies at this exceptional level 8 configuration. And in this picture here, you can convince yourself, right? So if this were in type 2a, then the red dots are T6 branes. I'm simply growing 2 S2s around each stack of T6 branes. These are going to touch in a point. And the M-theory lift of this configuration is that I have the 2 length spaces, and they touch along the full Hopf circle, which projects to this point. And this is what's called what I'm going to call the exceptional radial shell. And this exceptional radial shell is simply the deformation retraction here from left to right. If you want to squeeze this thing that I've been drawing as pair of pants into one radius slice, you're going to get this this gluing of the 2 length spaces. So here in equations, the radial thing is going to be, if I call the pair of pants V exceptional, it's going to be the deformation retract of V exceptional. Okay. And so some of the technicalities in this line of questioning is that I now need to start to compute homology groups of these kind of spaces, which are definitely not manifolds. They're just weird glued together things, but that's fine. That one can do and shouldn't be afraid of, and it gives the correct answers. So let's see some of this. Okay, so I want to explain the gluing conditions and the junction degrees of freedom a bit better. So on the 3 legs running into the junction, we have these fields, B2, N1, N2, and 1 plus N2, labeling the legs. The magnetic duals, which I'm not discussing now, is exactly the same as for this triplet. And in geometry, as Ami asked and we saw before, by standard dimensional reduction, these 3 two-form fields are in geometric correspondence with the Hopf circles in each of the S3 mod Zn1, Zn2, and 1 plus N2. And so to understand what happens with these field profiles as I go to the junction, I can simply track their geometric avatars across this pair of pans thing. And so a bit more formally, so there exist embeddings of the three boundaries into this pair of pans, simply include them as the boundary of the pair of pans. And then I can start taking cycles of each of these. I can drag them through the pair of pans. I can start comparing them, and I can see if they are the same and if I should be identifying for that reason their coefficients in some KK expansion. So this is, in words, what we're doing. We can compare the Hopf cycles in this common exceptional radial shell. And this gives gluing conditions, because these Hopf cycles are not independent, and the dependence relation in homology exactly gives you a gluing condition. And the gluing condition looks like this. So N1 over G times B2 N1 at the junction needs to be, oh, I just copied that, N2 over G B2 N2 at the junction, and that needs to be N over G B2 N at the junction. And this is an equation which results in ZG, and we'll see momentarily where that comes from. And so before I was harping on the junction being partially topological and partially physical, and this is the topological part of the boundary condition. Some B2 fields just glue across. Okay, this is just a picture of what we had before. And so we can count. So at the junction from the B2 field, we have roughly Zn1, Zn2, and Zn degrees of freedom. The boundary condition identifies these three. So there are two equal signs above. There is only the common profile left to fluctuate. And so the boundary conditions remove a ZG squared. And so now we have to supply more. These will be physical boundary conditions for the remaining degrees of freedom. And so now we have to do this computation of computing the homology and cohomology groups of the radial shells. This can be done using some algebraic topological techniques, most simplest of which would just be to cut it apart and glue it together and compute things using some Maya-Vietoris sequence. And so this is what you get. Let's focus on the cohomology groups. You can see that it's not a manifold because it has two top classes. And then the interesting part is what we're going to focus on here is the degree 2 stuff, which you would use to expand the G4 supergravity field strength. From the Z, you would get some U1 factor, which we'll turn to in a moment. And from the ZG, you get a ZG value 2 form living on the junction. And this is exactly the ZG value 2 form which mediates the gluing conditions I just showed you. Right, this is what I've stated here. Here written in homology. This ZG gives me the gluing conditions. And because it's a ZG, this equation ended up being an equation valued in ZG. This is why we had these fun prefactors of N1 over G, N2 over G, and N over G that took all these different fields, which might have which just might have different coefficient systems and basically map them onto a ZG values. Then we could compare them, and that's why they're reasonable to impose boundary conditions. Now, the other guy to talk about is this free 2 cycle. And if one analyzes the space a bit better, this one is going to be L copies of the exceptional curve that one introduced in resolving the space. And so it makes sense, well, you can just straight up compute. It gives you the U1 vector multiplet, which has to be localized at the junction. And from the perspective of this U1 vector multiplet, the question that we're going to answer now is, so let's center our perspective on the junction. Each of these fields, B2N1, B2N2, and B2N, I can just ask, what is their interpretation with respect to the junction? They should, via standard SymTFT law, be interpreted as background fields for some symmetry of the junction theory. And right, this is what I've written out here. Okay. And so this is what we do. And to make this a bit more precise, I'm going to restrict to a ZL. Well, it turns out that you can restrict to a ZL subgroup inside of the U1G. And let me denote the background with respect to this, to the one-form symmetry of the center ZL as B2L, superscript U1. And the point is that, again, standard SymTFT logic, that these three fields on the legs that we've motivated differently via the SUN factors are now given interpretations and backgrounds for this U1 one-form symmetry, which take values in this ZL. And if one does the computation, this is what these boundary conditions look like, or these identifications look like. So B2N1 can also be interpreted as a one-form symmetry background for the U1 with this coefficient, N2 over G. Right, and others as well. So N2, N1 over G, and if you do the arithmetics, it's exactly such that these are, so the first one, for example, is valued in Zn1, and the coefficient is exactly such that the whole thing is also valued in Zn1. And so these equations make sense for at least this way. And this part of the boundary condition I'm going to refer to as physical boundary conditions. And so we've now succeeded in mapping out the full sim tree. We have our vector multiplets at the red and purple nodes. We have fields on the SymTFTs in one higher dimension running between them. And I've told you exactly what happens at the junction. It's partially topological and partially physical. And okay, so what good is the sim tree for, and what limit does it hold? So first of all, so here's just the Higgsing data of what we've done, right? We've done an incredibly simple field theory manipulation. We've just done adjoint Higgsing. And so, for example, the adjoint representation decomposes like this into an adjoint representation and a bunch of bifundamentals with the indicated U1 charges. And similarly, the fundamental representation decomposes into the sum of some fundamentals. And you saw above that lowest common multiples appear, GCDs appeared, and you can get the charges and everything from computations of the sim tree. So, or the internal geometry corresponding to it. And so now the question is, in what limit is this sim tree a good description of the physics? And the sim tree is a good description in the limit in which the bifundamentals are heavy and you want to treat them as defects. And so here is exactly such a bifundamental. It's NEM2 wrapping the exceptional curve, or a fundamental string running between the D-brain stacks. And in the sim tree, it looks like a defect. So that's how it should be treated. But a nice property of now having expanded the adjoint Higgs theory in this limit of large Higgsing, here, this limit of large Higgsing into these additional branches, is that one clearly sees where all these parts of this defect running between the SUN1 and SUN2 theory come from. I can start out, for example, in the N1 theory. There, the first half of the line just looks like a standard Wilson line for that thing. It crosses through the junction, gives me a point there. And so there'll be a U1 Wilson line, which tensors to it. So it's going to be dressed by a U1 charge. And then it goes to the N2 part and picks up this. And similarly, decompositions hold for defects of the previous system, which I can decompose like this. Okay. Okay. So now you might be wondering, okay, he's just reformulated some adjoint Higgsing, which is not very deep, and he might have been using knowledge of the unhiggs theory. But part of the emphasis I want to make is that this is not the case. This geometric prescription that I've given works if the geometry does not have moduli, so that you can stack the singularities and go to some unhiggs theory. It works in complete detail. And so you can start building SymTrees for theories which have no point in the moduli space where they might be described by just a single SymTFT. So, right. So this is the one claim to fame. And then also, let me quickly go through this and then summarize. One can start now also analyzing compact X. If I have compact geometries, I'll be engineering a supergravity theory. So here's a very simple example, T4 mod Z2. It's going to have 16 A1 singularities, exactly singularities like we just discussed. And each of these is going to have 1670 SU2 super Young-Mills theories. And then very similar decompositions of this compact space now are going to give me SymTFTs which characterize the symmetries of these 16 theories as I glue them together into the compact geometry. And so the picture that I would want to draw for this T4 mod Z2 looks like this. I have a SymTree which has 16 SU2 things, and they all connect to a node. And then you can do some computation in this geometry. And for example, defects need to run between 4 of these nodes always. These defects will involve the U1 unless you take correct combinations of 8 of these. If you take defects which run between 8 nodes. And the point in the no global symmetry context here is that you can study how gluing the space together results in manipulations of the symmetries in each local model by gauging some symmetries, by adding matter, such that the resulting field theory sector has no global symmetries, and then, as of course manifests in string theory, can be coupled to gravity. Okay. And so let me now simply end with the summary and the main take-home messages, and also tell you what you might find in the paper that I have not talked about. So the main point of this talk was to introduce SymTrees. So they are just a collection of SymTFTs and interfaces between these. And as you saw in the example, you can tease out a bit more detailed structure of symmetries or of theories as you take certain limits of them. So the slogan is SymTrees organize symmetries. And the Higgsing example was one where we had some, we say, moduli flow to a system of the unhiggs theory. But so in the paper, you can also find examples where these things do not exist, and we discuss them at length, proving, well, going back to my point before, that you do not need these for the geometric prescription to work. And there's also some application to large and averaging in one of the later sections, where basically by identifying a favorable UV origin of some ensemble averaging setup in string theory, you can make sense of higher symmetries throughout this averaging procedure. And with that, let me thank you for your attention, and it was a pleasure.
All right, let's thank Max. Do we have questions? Let's see if someone is brave.
Oh. Okay. Any questions are welcome, or comments?
So,
yeah.
If you try to apply to theories with less supersymmetry,
yes,
what the differences do you expect to get?
Oh, this is a very interesting question, because you're very correctly noticing and pointing out that at no point I use something like a special holonomy G2 Calabi-Yau condition to derive any of this.
Or
and
even,
of course,
even add, just take this system and add M5 bytes, right? You could do that. And,
yeah.
Yeah. Mm-hmm.
So in principle, one can analyze these, but I need to give you a different prescription if the setup is no longer pure geometry. So a very interesting thing that I'm currently working on is, because symmetries are inherently topological structures, there is a hope, and this will also be the result, that you can now approach non-supersymmetric string compactifications, and these might be unstable, and via these topological considerations restrict the endpoints of these instabilities if they start evolving on you. So that is one application to the non-SUSY things. And I do not see an obstruction to, well, except for maybe technical ones, which I'm overviewing, not seeing now, to analyzing systems as the one you've just mentioned, Ami.
I see. Okay. Thank you.
Thanks.
More questions? All right, I would say let's thank Max again.
Thank you.
And we can move off the record.